Okay, this is Whitlock and Schluter Chapter 4 video lecture on confidence intervals. Now, the basic idea behind a confidence interval is it's an interval within which we have a high confidence that the true population parameter lies. Okay, so let's go right into an example from last time. We had samples of size 100 from the list of all human gene lengths, and we got this sampling distribution here, which ranges from roughly 2,000 to 3,500, say. And what's the true mean? Well, we actually know the true mean. It happened to be mu was 2,600. Okay, we would estimate that true mean using the center of this distribution, and that would be very, very close, 2614. If I went back in my example and I bumped that thing up to 500 and we redid it at 500, we should get even closer to the truth. And we've got 2624 and mu is 2622. So we are within 2 using this process. And this is an unbiased process that converges upon the true mean using sample means, which is remarkable. And so here's what we're going to do then. We're going to take an interval within this sampling distribution, and in that interval we're going to say whatever percentage of the data is in there, that's how confident we are that our interval contains the true unknown mean. To illustrate confidence intervals, we're going to start with a 95% confidence interval, which is the usual level. We'll show how to change it later. And in a particular case, we'll just suppose that we had a sample mean of 2,411. That is x bar equals 2411.8. Now it turns out that the confidence interval in that particular case was 2119.2 to 2704. I've got a 0.4 on there. Now, what that means is we're 95% confident the true mean length, not an x bar, the actual mu of a gene is in that interval, 2120 to 2700, roughly. Okay, now, how do we get that? We're just doing the general, but for right now, our basic confidence interval is the sample mean plus or minus 2 times the standard error. In this particular case, we used standard error 146.3, and so you'll get that 2411.8 plus or minus 2 times 146.3 is going to give this interval up here. Okay, now for an actual example from our particular case. I'm going to run back here and do a simulation. We were running last time a sample of size 500. This time we're going to do samples of size 1,000. And let's remind ourselves what we're doing. We're taking 1,000 samples of size 100. And then we're going to generate a histogram of the 1,000 means. Roughly mound-shaped. The right side is, we're going to skew a little bit on the right. Okay, now we're going to use the very last sample that we took, which was x. It was the 1,000th x. So I'm going to just take a look at it. Here's x. I've got 100 observations on x. You can see them there. In reality, that's it. That's all I've got is a sample of 100 observations. Let's do the interval. Here it is. Mean of x is right there, 2784. Standard deviation of x is 2,228. So I'm recording those numbers, 2784 and 2028. Now, let's go and run the calculation. We'll do it here for simplicity. The SDE is just going to call standard deviation of x, and then we're going to divide it by the square root of our sample size, which, as we know, is 100, so that's easy. And then we're going to take, let's call x bar equal to mean x, so x bar minus SD 2 times SDE, and x bar plus 2 times SDE. That gives me 2378 to 3190 as my confidence interval. Now, how did I do? Is that in range? Well, of course we know that that mu itself is 2622. Is mu inside of there? Yes. Therefore, my confidence interval contained the true unknown mean, which was 26,022. Okay, last thing I'd like to do is illustrate this on a wider scale. Now, what I'm going to do is compute 20 confidence intervals. All together, we're going to use samples of size 100, and we'll just run this process real fast. I'm going to get a mean and a standard deviation for each one. We're going to calculate standard error, and then I'm doing, you can see x bar minus 2 standard errors, x bar plus 2 standard errors. That's the calculation. So watch this. We're going to stick them all together in one shot. I need to widen my view. Let's try that here. And in dot out with the data frame. Oh. Okay, we've got ourselves 20 confidence intervals, and one of them was 2499 to 3405. Did that contain the true 2600 and something? Yes. And so I've automated to answer yes, 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 no. Boom, what happened? 2701 to 3414 did not contain the true unknown population parameter, which we actually know, so we can check this. And here's another one that didn't, was too low. Here's another one that was just a hair too high. Out of 20, we had 3 miss. On average, we should have 1 miss. 1 over 20 is 5%. Let's try that again. Is it just a fluke that we had 3 miss? According to this process, on average, we will miss 1 out of 20. Here's one where we got only 1 miss and it was too low. We'll try one more time, and you can practice this experiment yourself if you want with the script. Here's another one. Look at that. We got all yeses. So in the long run, this will average out to 5% no's, 95% yeses.